Hi guys, in this video we'll take a look at more complicated composite functions, indefinite integration by substitution, definite integration by substitution, examples, and then we'll finish with a summary.
So how can we integrate more complicated general composite functions? We have met a number of different rules to help us integrate composite functions. In particular, we've seen the inside function rule. This is the rule that the integral of f of ax plus b is equal to 1 divided by a multiplied by capital F of ax plus b and then plus c, where capital F is the integral of little f. Similarly, we have met the product reverse chain rule. There is also the quotient reverse chain rule, but for now, the product reverse chain rule is that if we have a function f and we have the derivative of f multiplied by f of x to some power, say power n, then this is equal to f of x to the power of n plus 1 divided by n plus 1. And as always, we have our plus c. Sometimes none of these rules of integration can be easily applied when integrating some more complicated composite functions. For example, how would you integrate e to the power of cos x using these rules? E to the power of cos x is not of the form f of ax plus b, nor is it of the form f prime of x multiplied by f of x to the power of n. And as such, we cannot use either of these rules in order to calculate this integral. We can alternatively integrate a composite function by looking at a way of changing the variable to simplify the integral. Let's say we were asked to integrate x multiplied by x minus 1 all cubed. What we do is we change the variable. We let the variable u be equal to x minus 1, and then what happens is we entirely change variables from x to u. So we have this x multiplied by x minus 1 to the power of 3, well, this becomes u to the power of 4 plus u to the power of 3. And it turns out that we can then integrate with respect to u, and these are just terms of a polynomial, which are very easy to integrate. This process is called integration by substitution. We substitute u for x. U is equal to x minus 1 in this case. Instead of writing x minus 1, we substitute x minus 1 for u. So how do we do indefinite integration by substitution? When asked to calculate a complicated indefinite integral, we can try to simplify it by changing the variable and performing a substitution. Let's say we have the integral of x multiplied by the square root of 2x plus 1. We are going to substitute from x to u. Usually, the question will tell us which substitution to use. This isn't always the case, but we may see something of the form use the substitution, say in this case, u is equal to 2x plus 1. If we are not told which substitution to use, we should look for a composite function and substitute for the inner function. As I said, sometimes they do not tell you the substitution to use. And so let's say we're given this square root of 2x plus 1, which we have in this case. This is a composite function. We have the 2x plus 1 all to the power of 1/2, the square root. And then we look at the inner function inside that composition, and we substitute u equal to that inner function, 2x plus 1. The chosen substitution should then be differentiated, and we can write dx in terms of du. The whole idea is to completely remove x's from our integral we have, and turn them entirely into u's. This includes the dx. We're going to want to integrate with respect to u. And so a nice way of doing this when we have our u equals 2x plus 1 is to consider the derivative du by dx. All this is saying is to take our u and differentiate it with respect to x. Well, this is the same as differentiating 2x plus 1 by the definition of u. Differentiating 2x gives us 2, and differentiating 1 gives us 0, and so we just have 2 for du by dx. Now, we should not really treat our du by dx as a normal fraction. It is a derivative, but in this particular case, it works out that we can, and we can rearrange this to make dx the subject. We get that dx is equal to 1/2 du, just by rearranging. We are now able to replace dx by the expression in terms of du, and any clear occurrences of u in the integrand. So at first we have the integral of x multiplied by 2x plus 1 square rooted, and this is currently with respect to x. And then our first step from here, now that we've got all this information, is that we can substitute wherever we see a u, and we now have our equation for dx in terms of du, and so this becomes the integral. For now we'll include this x here, we're going to change that in a minute, and then we have the square root of u now, because instead of having the square root of 2x plus 1, we have let u equal 2x plus 1, and then we multiply this by dx. And again, we're trying to remove the x's, so we use our equation dx equals 1/2 du, and then we have our 1/2 du. It is a good idea to simplify as far as possible at this point, and then write any remaining x terms in terms of u. So currently we have the integral of x multiplied by root u, and then we have this multiplication by 1/2 du. We can instead put the half with, say, the x, and we get the integral of x divided by 2, and then we have our root u, and then we have our du. Now, we look at our substitution, u is equal to 2x plus 1. We can rearrange this to make x the subject, and then substitute that in. So we have that x is equal to u minus 1 divided by 2. And then we can substitute this in, and we get that the integral of x multiplied by the square root of 2x plus 1 dx, which is what we started with, is equal to, instead, by bringing the 1/2 in and including it with the other 1/2, 1/4 multiplied by u minus 1 multiplied by the square root of u du. Now everything is in terms of u, and we can now perform this integration. The integral can now be found in terms of u. What we do is we take our integral, which is the integral of 1/4 multiplied by u minus 1 multiplied by root u, and then we have our du. We can now see that our du's and dx's play a much more important role in this process of integration by substitution. And then we can use the linearity of integration to bring the 1/4 entirely outside of the integral. And we have our integral symbol. And then we can distribute the root u, or u to the power of 1/2, to each of the terms in this bracket. U multiplied by root u is u to the power of 3/2. And we have our minus 1 times root u is u to the power of 1/2. And then we have our du. Now we are able to integrate these terms. This is a lot easier to do. We add 1 to the power and divide by that power, so we get u to the power of 5/2 divided by 5/2, and we still have this 1/4, and so we get 1/10 multiplied by u to the power of 5/2, and for the next term we get minus 1/6 u to the power of 3/2. And then, as always, this is indefinite integration, and so we have our plus c. As we are finding an indefinite integral, the answer is an expression, and so should be rewritten in terms of the original variable x. At first we were considering the integral of x multiplied by 2x plus 1 square rooted, and of course we have our dx, which is very important now. And we have found, as above, that this is equal to 1 divided by 10 multiplied by u to the power of 5/2, and then we minus 1/6 multiplied by u to the power of 3/2. And of course we have our plus c. But we expect that when we integrate a function of x, that our answer will be a function of x. And so now we resubstitute back in our expression for u. U is equal to 2x plus 1, and so we get our 1/10 multiplied by 2x plus 1 all to the power of 5/2, Again, all we've done is to put our 2x plus 1 everywhere that we see u, and then we have a minus 1/6 multiplied by 2x plus 1 to the power of 3/2, and then as always we still have our plus c. This is the result from the integral, and it became much easier to do when using this method of integration by substitution. So how can we do definite integration by substitution? We can similarly use the substitution method to calculate more complicated definite integrals. Let's say we were asked to find the value of the integral between 4 and 5 of 2x multiplied by the square root of 5 minus x. And of course we have our dx. Now we may be told the substitution, or we may use our method we described before to guess the substitution. A good substitution in this case will be u is equal to 5 minus x. This is the expression inside our composite function. We should start by changing the limits of the definite integral from x to u. This is the main difference with definite integration by substitution. We have that u is equal to 5 minus x. And so we take our limits. The first limit is x is equal to 4, and the second limit is x is equal to 5. Now notice that I write x is equal to these limits. I write this because these are limits of the x integral. We are integrating with respect to x. Soon, based on our substitution, we will be integrating with respect to u, and so we need to find the u limits. We simply do this using our expression for u in terms of x. And so for our first one, we get u is equal to 5 minus x, well that's 5 minus 4 for this value, which is 1. And similarly, for x is 5, we get u is equal to 5 minus 5, which is 0. We are also required to write the integrand in terms of u, like we did before, changing the integral to be written with respect to u, and using the new u limits. So again we have our substitution, u is equal to 5 minus x. The first thing we should do, because it'd be useful for later on, is to write x in terms of u, and then we can substitute that right at the end. And so we get that x is equal to 5 minus u. Similarly, we should differentiate u with respect to x in order to find du by dx, and hence we can then substitute that for dx in terms of du. So we have first du by dx, and just by differentiating u with respect to x, we're going to get minus 1. These are the two very useful bits of information we're going to need to perform our substitution. And so our integral from 4 up to 5 of 2x multiplied by the square root of 5 minus x, and then we have our dx. This now becomes very simply, first we examine the limits. Our new limits are, and now it's very important to have this in the correct order, our new limits are 1 and then 0, in the almost counterintuitive opposite order, 1 at the bottom and 0 at the top. This is correct, however, despite being unintuitive. Then we look at our dx, and we want to have du instead. Well, du equals minus dx, so dx is minus du, whichever way around you want to put it, and so if you want to have a du, we're going to need to have a minus with it, and so I'll put that minus at the front. And then we have our 2x, well that is 2 lots of 5 minus u by substituting. And then finally, the whole point of this, we have our square root of u. The definite integral can now be calculated, but with respect to the new variable u instead of the old variable x. We are now looking at the integral between 1 and 0 of minus 2 lots of 5 minus u multiplied by root u du. First we can then expand out. We have the integral between 1 and 0 of minus 10, and then we have our u to the power of 1/2, and then we have a plus 2u to the power of 3/2, and we have our du, but this is around the whole of the expression. Now we can perform our integration with respect to u, and so we get our square brackets, and then we get minus 20 over 3 when you work out the constant, multiplied by u to the power of 3/2, and then we get a plus 4 over 5 multiplied by u to the power of 5/2. Close our bracket, and then we have 1 here and 0 here. Then we substitute in, well, substituting in u equals 0 into this expression will just give 0. And then we subtract the following expression. And again, when there are only powers involved, substituting in 1 just leaves the constant, since 1 to the power of anything is 1. And so we get a minus 20 over 3 and a plus 4/3. This gives us 88 divided by 15 for our answer. Let's take a look at some examples. Our first example asked us to use the substitution u is equal to 2x minus 1 to find the definite integral, the integral between 2 and 3 of 6x multiplied by 2x minus 1 all cubed. Our first step is to write down the substitution we're going to use. By looking at the composite function involved, 2x minus 1 to the power of 3, it is a sensible choice to use u is equal to 2x minus 1. Now, in this case, this was a given, but in general, that is why we'd reason that is a good substitution. Our second step is to differentiate the substitution by differentiating u with respect to x. We obtain du by dx, and we are going to get just 2. Our third step is to replace dx by the expression in terms of du and change the limits from x to u. By rearranging the above, we get that dx is equal to 1/2 du. Now, using our substitution u is equal to x minus 1, we can find the new limits. When we have x being equal to 2, we have that u is equal to 2 lots of 2 minus 1. This, of course, is 4 minus 1, which is 3. Similarly, if we have x is being equal to our upper limit, which is 3, then we get that the value of u corresponding to that is 2 lots of 3 minus 1, which is equal to 6 minus 1, which is equal to 5. And so therefore, our integral, which is the integral between 2 and 3 of 6x multiplied by 2x minus 1 all cubed dx, is now equal to the following. We have the integral between our new limits, which are in the correct order, 3, because 2 corresponds to 3, and 5, because 3 corresponds to 5. And then we have our 6x multiplied by 2x minus 1 all cubed. And then the only change we're going to make here is transforming dx into du, and so we get a 1/2 du. Our next step is to write x in terms of u and replace any terms containing x by terms containing u, simplifying the integrand as far as possible. We have that our substitution is u is equal to 2x minus 1, and therefore by rearranging we get that x is equal to 1/2 multiplied by u plus 1. So then we can use this in order to substitute further, and so we take our integral, which is now currently, if we simplify the 6 and the 1/2, we have the integral between 3 and 5 of only 3x, rather than 6x due to the 1/2, and then we have it multiplied by 2x minus 1 all cubed, and this gives us our du this time. And all we do now is to substitute everywhere for u. So we have the integral with the same limits, we already sorted out those before, but now we have our 3 multiplied by our x, which is 1/2 lots of u plus 1, and then we have our 2x minus 1 all cubed, well that is just u cubed, and then we have our du. This is going to be, if we bring the constant outside, 3 over 2, and then the integral from 3 up to 5 of u plus 1 multiplied by u cubed, well that is u to the power of 4 plus u to the power of 3. And then we have our du. The fifth step is to write the definite integral in square bracket notation by integrating the expression. So again, originally we were integrating between 2 and 3, 6x multiplied by 2x minus 1 all cubed, and of course a dx. We've now transformed this into 3 over 2 multiplied by the integral from 3 up to 5 of u to the power of 4 plus u to the power of 3 du. And so we perform the integration and we leave our 3 over 2 outside, and then we have our square brackets we get a 1/5 u to the power of 5, and then we have our plus 1/4 u to the power of 4. And then we have our new limits 3 and 5. Our last step is to calculate the value of the definite integral. So again, this is the integral between 2 and 3 of 6x multiplied by 2x minus 1 all cubed, and then dx. And we've reduced it to substituting in these values based on this square brackets. And so we get, of course, 3/2 multiplied by these square brackets, and we have our 1/5 u to the power of 5 plus our 1/4 u to the power of 4 with our limits of 3 and 5. And all we need to do now is to substitute in, and so we leave our 3/2 outside the expression, and then we get a 1/5 multiplied by 5 to the power of 5, and then we have a plus 1/4 multiplied by 5 to the power of 4, and then we do the same thing for 3 but by subtracting it off, so 1/5 multiplied by 3 to the power of 5, and then we plus 1/4 multiplied by 3 to the power of 4. And we work out this whole value and we get to one decimal place 1068.6. Our second example asked us to use the substitution u equals tan x to find the integral of sec squared of x multiplied by tan squared of x dx. Our first step is to write down the substitution we're going to use. We've been given the substitution u is equal to tan x. Now, we could reason why this is a good substitution. It is because, in fact, sec squared is the derivative of tan x, and we'll see why this is useful in a moment. Our second step is to differentiate the substitution by differentiating u with respect to x. We get that du by dx is equal to sec squared x, and this is precisely what will be useful in a moment. Our third step is to replace dx by the expression in terms of du, simplifying the integrand as far as possible. By rearranging, we get that dx is equal to du divided by sec squared x. And so we have the integral of sec squared x multiplied by tan squared x dx. And by substituting, this becomes the integral of sec squared x multiplied by u squared, because u is equal to tan x. And then we have a du divided by sec squared x. This is the property which is particularly useful. We now have the integral of u squared multiplied by du. It was useful because we divided off the sec squared in our dx expression. And now this is an integral we can indeed evaluate. Our fourth step is to find the integral in terms of u. We are looking in general at the integral of sec squared x multiplied by tan squared x dx. And we have reduced this to the integral of u squared with respect to u, i.e. u squared du. And just by very simply integrating, we get a u cubed plus c. Our fifth step is to rewrite the integral in terms of x. Again, we're looking at the integral of sec squared x multiplied by tan squared x dx. And just by back substituting our expression for u, we substituted u was equal to tan x. And therefore, by putting this back into our expression, we have u cubed plus c, which is going to be tan cubed x plus c. Our third example asked us to use the substitution x equals e to the power of u to find the indefinite integral, the integral of 1 over x ln x dx. Our first step is to write down the substitution we're going to use. We have, and we've been given, x equals e to the power of u. Now, one thing to note is this is not directly in the form we're used to. We're used to having u as a function of x, but this is implicitly u in terms of x. We could, in this case, rearrange to get u is the natural logarithm of x, but it is not necessary, as it'd be quite nice in this way instead. And also it's good for illustration to show that you can do it in this way as well. And so our second step is to differentiate the substitution by differentiating this time x with respect to u. So this time we're going to consider dx by du, and of course we're going to get e to the power of u by the very nature of the exponential function. Our third step is to replace dx by the expression in terms of du. By rearranging, we get that dx is equal to e to the power of u du. And so we take our integral, the integral of 1 divided by x multiplied by the natural logarithm of x, and then we substitute in, and we have the integral of e to the power of u, and then we divide by x ln x, and now we have our du. Our fourth step is to write u in terms of x and replace any terms containing x by terms containing u, simplifying the integrand as far as possible. So originally we had that x is equal to e to the power of u, and then we rearrange this, as we said, to get u is equal to the natural logarithm of x. And this is quite nice, because in this case it means we can substitute that in to there, in the denominator. And so in general we're looking at the integral of 1 divided by x ln x, and we develop this to have e to the power of u divided by x multiplied by ln x, and then a du. But now we have more than enough information to perform the substitution and only end up with parts that are functions of u. And so we have the integral of e to the power of u on the numerator. Our denominator is e to the power of u, because that's what x is by our substitution we did at the first. And then we now know that ln x is u, and so we can substitute that in to have a u there, and then we have our du. But in fact the e to the power of u's cancel out on the top and the bottom, and so we just end up with 1 divided by u and then du, which we know how to integrate. Our fifth step is to find the integral in terms of u. We have the integral of 1 divided by u du, and this, almost by definition, is equal to the natural logarithm of the modulus of u and then plus c. Our last step is to rewrite the integral in terms of x. We were examining the integral of 1 divided by x multiplied by the natural logarithm of x, and then dx. This is equal to, we found, the natural logarithm of the modulus of u plus c. This is the time I guess it's quite useful to have it u in terms of x. And then we look at the above, and we see that we have u in terms of x, u is equal to the natural logarithm of x, and therefore we get the natural logarithm of the modulus of the natural logarithm of x, and then plus c. This is our final answer for the integral.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level maths a walk in the park.